Alright, this is the first lesson in thermal effects. First of all, in this it's built on a thing called the kinetic particle model. So, kinetic particle model. And so, it's when we're looking at the thermal effects, what we're doing is in relation to the particles in the substance and what those particles are doing. So, first of all, in your notes on your first page there, it talks about the particle model and how it works. And so there's 5 dot points there, and in those dot points it talks about what we understand the particle model. So these particles have got to be very small. The other thing that we consider is that they're in constant motion, so always moving. That kinetic energy is not lost in collisions between those particles. That won't mean much to you now at this point, but just suffice to say that energy doesn't disappear. And the other thing is that there's forces, both attracting and repel in the force between those particles. And in terms of distances between particles in comparison to the particles in the space between them, so there's large distances between particles. Alright, so in the kinetic particle model, that's what we consider that those particles are doing. Alright, so the model is based on those things. So the model can be used to explain the states of matter. Okay, and the states of matter, first of all, is solid. So in the solids there's a balance between the forces. Okay, so because there's a balance, the particles are in fixed position. Alright, so if there wasn't a balance between the forces, then the particles would move out of position and it wouldn't be a solid. It would be a liquid. And so in the liquid, the particles can move more. Right, so some of these words are the ones that are in your gaps there that you've got to fill in. So particles move more. And then in the gas, but there's still some attraction there. But in the gas, what we've got here is we've got random motion. So the forces are not strong enough to hold the particles together, and so they move around. So weak forces between particles. All right. So that's the assumption there on the kinetic particle model. They're our three states of matter, and then in terms of particles and those assumptions that we've made, in particular for the states of matter, the forces between the particles. All right, so the next thing is thermal energy. All right, there's a whole bunch of energies. Thermal energy is, if you like, heat energy, and most of our thermal energy originates from the sun. Okay, so, you know, days are warmer than nights and those sorts of things. Days when the sun's out are warmer than days when the sun's behind the clouds, those sorts of things. So most of ours comes from the sun, and then some of that's converted to other sources, and there are other ways that we can get thermal energy. We've all got heaters in our houses and things like that. All right, so the next thing we've got to look at is temperature and heat. Now, temperature and heat in terms of physics and science and thermodynamics aren't exactly the same thing. So, heat, for example, is a measure of thermal energy. Alright, so thermal energy, heat energy, thermal energy. Alright, so, and that thermal energy gets transferred between our particles. And so, for example, they're not exactly the same. So, for example, if I have a pin and then I get and heat that up with a match or something, then that tip of that pin is going to get to a very high temperature. But then what's going to happen is it's going to cool very low, so it's got low heat energy. But if I have a cup of coffee or something like that, for example, then it's a low temperature, but it's going to have high heat energy. So, like, what's the difference between those two things? Well, the difference between those two things is the atoms. So in the pin, you haven't got very many, and in the cup of coffee, you've got a lot. So the temperature here really refers to the individual atom or the individual particle. So if there's high temperature, those individual particles are moving around a lot, and low temperature, those individual particles aren't moving around very much. But in terms of the energy, in the pin there's not many particles, pin particles, but in the coffee there's lots of coffee particles. So that's where the heat difference is. All right. Now, the other thing that happens is that with your heat, again, it's the thermal energy transferred. Now, what happens there is that we define it as heat energy, or thermal energy, I've got something that has a high temperature, for example. So you've got a glass of water that's warm, then it's got a bit of thermal energy in it. If you then get some ice, which has less thermal energy in it, so by definition, when we put the ice in that, then the temperature of the ice and the water comes to some sort of equilibrium, but by definition, the thermal energy transfer that's occurred there has been from the high temperature or the higher temperature warm water through to the lower temperature ice, and the particles in that ice move around and it changes its state. You get to changing state. All right, now the only other thing that I haven't mentioned, thermal energy, because it is energy, and all energy is measured in the unit joule. After joule, that's what happens when you become a famous scientist. You get things named after you. So the unit for thermal energy, heat, is joule. All right. So that's about heat. Now this is temperature. All right. So temperature, as I've mentioned before, it's about the kinetic energy of individual particles. Alright, so in the pin had high temperature because those particles that were on the tip of it were moving around a lot. Alright, so they have high kinetic energy, and the faster they move around, the higher the temperature, the more the kinetic energy. There's a few different measurements of temperature. One we use in everyday life is Celsius, so degrees Celsius. That works off water. The freezing point is 0 and the boiling point is 100. So that's one of them. And if I spell it right, another one is that we don't use, but it's used what's called imperial measurements, is degrees Fahrenheit. There is a relationship between degrees Fahrenheit and Celsius, and that's degrees Fahrenheit is 9/5 times degrees Celsius plus 32. So those countries like the US that still use imperial system use Fahrenheit. We use Celsius, the metric countries. And in science, there's another one called Kelvin, after Lord Kelvin. And Kelvin is so special it doesn't have a degree sign, it's just called Kelvin. And 1 degree Kelvin and 1 degree Celsius are the same. But what we have is that Kelvin is degrees Celsius plus 273.15 is our current best estimate. But for us, what we're going to just use is that Kelvin is degrees Celsius plus 273. Alright, so scientists use Kelvin, so that's significant, and theoretically, although that has not yet been achieved, but theoretically we have a 0 degree Kelvin, which is the lowest possible degree that you can have, and apparently at that point, theoretically, you've removed all energy from the system and the atom ceases to exist as we know it. All right, so that's a couple of definitions there from those things. All right, so next we move on to the laws of thermodynamics. Alright, and there is a video that you need to watch, or you can watch that talks, it gives you some more information, and that's called thermodynamics. And that goes through a few things. Alright, so there's some laws, and there's actually 4 laws, but they're not called laws 1, 2, 3 and 4. That's a little bit of a anomaly. So the first one that's important is called the zeroth law. So, common question you get there is, why isn't it called the first? Well, it was actually thought of after the other 3. So they decided it was more important though, so that they then put it at the front and called it the zeroth. Alright, so what the zeroth law relates to is thermal equilibrium. Alright, so thermal equilibrium, so if we have 2 objects of different temperatures, so we've got high temp and a lower temp, what you'll have is you'll have a flow of energy between them. And as I mentioned, from the high to the low temperature. And then when they reach thermal equilibrium, after that energy's flowed from one to the other, got out of spell there for a second. So thermal equilibrium, what that implies then is that our objects have the same temperature. Alright, so that's the zeroth law. Alright, so they decided that that was the most important law after they were doing some other stuff, and they kind of thought, yeah, okay, well that's pretty obvious, isn't it, that that should be the case. Let's put that at the start. Alright. So the first law of thermodynamics is basically it's about conservation of energy. Alright, so there's conservation of energy, as we'll see in all kinds of situations with energy, we'll see through the course, but in particular this one relates to thermodynamics. And so what it says is that if you have a change in the internal energy of something, of an object, one of 2 things must have happened. So one of those things is we get heat added, or removed, from that particular system. The second thing, so by adding you can heat it up, removing it you can cool it down. or you can do work on the system. And whilst beyond this course, gas laws there, some of the gas laws, if you compress gases and things like that, their temperatures can change. So in your notes there on page 2 down there under the first law, it says, the change is equal to heat added to the system minus work done by the system. And symbolically, delta U, which is our change, in internal energy, equals Q, which is our heat energy, minus W, which is work done by system. Alright, now a little bit of a note, and this is a little bit of an anomaly, and chemistry actually view this differently, but work done on the system, so you'll notice here it's by the system, but work done on the system. Right, work done on the system is considered negative. I know it's a bit weird, and why is it like that? It would be nice if it wasn't, but that's what these scientists decided in the first place, so there we go. Alright, let's have a look at a couple of examples and then we're on to our first set of questions. So example 1, so we're on about page 3 here now, so we've got a litre of water. There's work done on it. So work done on it, as I mentioned in the previous slide here, work done on is negative. So the work done on it is negative 25 kilojoules. Better go back on that one. Kilojoules. And it loses, so that's Q, thermal energy, Q loses, again, negative 30 kilojoules. Change that and make it right. Alright. So, if change in the internal energy is Q minus W, so the change in is negative 30 kilojoules minus negative 25 kilojoules, negative and negatives are plus, so negative 30 plus 25 would be negative 5 kilojoules is the change in the internal energy. Alright, example number 2 there, it says student places a heating element and a paddle wheel in an insulated container. She calculates that the water has, should say there, that the water has 2,530 joule of thermal energy, and the paddle wheel does work on the system. And remember again, back here, work on the system is negative. So the paddle wheel does 240, and because it's done on, and so again the change in energy of the system would be 2530 minus negative 240 equals again plus 2770 joule. Okay, so that question doesn't read very well there. So places a heating element in the paddle wheel. She calculates that the water gains, it should say, that much of thermal energy from the heating element, and then of course the paddle wheel doing some work also. All right. I think that's it. That's all there is to the first one. So now we're at problem set number 1. It's on there, and they're text questions. So you need to go to your text there and do those questions on page 9.